Hello, welcome back to Physics 1. In this lesson, we're going to be calculating the vector magnitude and the angle. And this is part one of a few different lessons. So what we're going to do in this lesson is continue working with vectors and learning how to calculate the magnitude and angle. Next lesson, a few lessons after this, will be adding vectors, learning how to add vectors, but using components to do that instead of the graphical way that we did it before. And then we'll finally start getting into motion along one direction. What does motion look like? What does acceleration look like? And getting into more of the physics concepts. But this is crucial stuff because all of those motion problems, force problems, are all going to have vectors. So remember, in the last couple of sections, in the previous set of lessons, what we did is I gave you the magnitude and the angle of a vector, and I asked you, give me the x component, give me the y component. We call that breaking a vector into components. In this lesson, we're going to go exactly backwards. I'm going to show you how, if you're given the x and y components of a vector, how do you figure out the magnitude and the angle of the vector? Because remember, there's always two ways to describe a vector. You could describe it in components, x and y component, and we can also describe it in magnitude and direction, magnitude and angle. So here we're going to go backwards, where I give you those components first, and we go backwards. So as an example, let me just do it with a graphical example. What we're going to do, actually, to give you the ultra roadmap, is I'm going to give you four different vectors, two in this section and two in the next section. We're going to do one vector in this quadrant, one vector in this quadrant, one vector in this quadrant, and one vector in this quadrant. And in each of those cases, I'm going to give you the vector, right, in terms of its components, but we want to go back and find its magnitude and direction. So what do I mean by that? I'm saying here's some vector here. Let's call it vector f. I'm going to generally use force vectors because I think they're easy to understand. Everybody knows that you push on something with a force. So this is some force that you're pushing on something or whatever. And you can break any vector into components. And so we have the components of this vector, right? So this component, this direction, let me draw right under the axis to show you from here to here. We call that f sub x. And I'm going to give that to you. I'm going to tell you it's 4 newtons. All right? And then this component going up like this is called the y component, so we call it f sub y, and this guy is going to be 3 newtons. So you can see I tried to make this arrow a little bit longer than this one. I haven't gotten a ruler out or whatever, but you can see the general idea. So in the previous set of lessons, I gave you the length of the vector, the total vector, and I gave you its angle, and we calculated these components. Now we're going exactly backwards. I want to give you the components and make sure that you can tell me the magnitude and the direction of the original vector, the composite vector that's the sum of those two components. So you notice that every one of these vectors forms a right triangle. Every time you draw a vector and break it into components, it's always a right angle here. So Pythagorean theorem always applies to vectors. So the way that you find the magnitude of the vector, the way you write it down is you say, I'm going to find the magnitude of this vector f, the length of this arrow. It's just the Pythagorean theorem. So what you say is, because this squared is equal to this squared plus this squared, the way you really write it down is you say that the length of that vector is going to be f sub x squared plus f sub y squared. Now in the problem statement, I already gave you fx and fy. I told you what the components are. So all you have to do is stick them into the Pythagorean theorem here, and then what you will see is that what you get is the square root of fx is 4. Go ahead and write it as 4 squared for now. And this is 3, so write it as 3 squared. Don't do too many steps at once. I want to see that you're squaring this and squaring this. And so what do you have? 16 plus 9. So again, don't do everything at once. So 16 plus 9, go ahead and keep it under the radical like that so that your teacher can see exactly what you're doing. So what we're saying is that this is equal to, what is 16 plus 9? It's 25. Which equals 5. The square root of 25 is equal to 5. 5 times 5 is 25. So what you have found is that the magnitude or the length of this composite vector f, which is some force, is 5. Now, we're going to call it 5 newtons. Why? Because we said the x component was 4 newtons, the y component was 3 newtons, so this composite thing is 5 newtons. So that literally means if I were to draw this to scale 4 units long, and draw this one 3 units long, and then connect the resultant, notice this is a vector addition here, connect the resultant with a ruler, I would measure exactly 5, because it follows the Pythagorean theorem. So anytime you're given components, x component, y component of a vector, the magnitude, to find the magnitude of the vector is very simple, and it's always done the same way every time. You use Pythagorean theorem. So the length of the vector is the square root of each side squared, you square them, then you add them up, then you take the square root. It's better to show every step separately so you don't make any mistakes. Now, how do we find this angle? What angle am I talking about? I'm saying that this angle, this vector f, is defined by its length, which we know, we just calculated what that is, but it also has some angle, we call it theta. The angle is usually measured from the positive x-axis, as it has been in all of the other problems. So how do we use this information that we're given in the problem to find the angle? Well, it's a triangle. Just like any right triangle, you can use sine, cosine, or tangent. But if you remember back from what we talked about before, the tangent function in our review of trigonometry involves the opposite side and the adjacent side. So to find the angle here, given the components, you're always going to use the tangent function to find this angle. And so the way you write it down is you say, let me go ahead and put a little line here since we're kind of done with the first part of the problem. The tangent of this angle theta is equal to what? The tangent function is opposite over adjacent, so 3/5. So literally, the tangent of the angle, whatever the angle is, it's unknown, is equal to 3/5, okay? Which means it's equal to, oh, not 3/5, 3/4, sorry, 3/4. 3/4, because that's a 4, which means it's equal to 0.75. So if you stick 3 and divide by 4, of course you're going to get 0.75. So how do we find this angle here? The angle is wrapped up inside the tangent function. So you undo the tangent the same way you do any equation. You do the opposite to get rid of this guy. So the opposite of a tangent is an inverse tangent. And so if you apply the inverse tangent to the left, it'll get rid of the tangent. And if you apply the inverse tangent to the right, well, right now I'm just going to write it as inverse tangent 0.75. So what I'm going to do is take the inverse tangent of the left, that gives me the angle theta, which I'm solving for. Inverse tangent of the right is what I'm writing. So on your calculator, type in 0.75 and then hit the inverse tangent button. Make sure your calculator's in degree mode. For most of the problems in physics, we'll be dealing with degrees. If it's in radians, you'll get a radian answer and you'll have to convert. So stick this in, inverse tangent, what are you going to get? It's going to be 36.87 degrees. Now, here is, let's just take stock of what we've done. The angle here is 36 and some change. That makes sense with what we've more or less drawn. 4 units long, 3 units long. This angle looks to be about 30-something degrees, so it seems to make sense. Also, notice it's a positive angle. The answer we got from the calculator was a positive angle. Angles in trigonometry are always measured from the positive x-axis. Certainly any angle that your calculator gives you back as an answer, like an inverse tangent or an inverse sine or whatever, it's always going to be measured relative to the positive x-axis. So it makes sense. So the one thing I want to caution you to, because we're going to see in the next section, I'm going to caution you even more when you get a little bit of a weird answer. Finding the magnitude of these vectors is very simple. Finding the angle of the vector, you have to be careful. I'll say that one more time. You have to be careful. What you have to do is, when you take the inverse tangent and find the angle, you have to go back up to your drawing and make sure that the angle makes sense. In this case, it did make sense because 36 degrees is about equal to what we have in here, and it's a positive angle, which means it's a positive angle measure in the drawing here, so everything matches. You don't yet understand why you have to be careful because I haven't shown you why. But in the next problem, we'll do exactly the same calculation with a different vector, and you will see that this can get a little tricky sometimes. In this case, it made total sense. So what you're really doing is you're looking for a sanity check on the angle to make sure it's right. Everything's correct as is in this problem. Now let's go to the next problem, which is, like I said in the beginning, we're going to do the exact same type of calculation. So I'll call this, I guess, number 2. We're going to do the exact same type of calculation, except this one is going to be in another quadrant. So this is x and y here. Notice that for the previous problem, we had a positive x component, a positive y component. And because of that, it defines a vector in quadrant 1, which means the angle's positive, and so the angle's positive is measured from the x-axis. Everything's cool. Now let's go back and draw another vector. This one we're going to draw in quadrant 2, which means we're going to be over here. Let's just make it this long, just to make it easy. All right, this vector is going to have, let's go ahead and draw a dotted line here. And we'll draw a dotted line right there. And then we'll say this guy, what is the length in this direction? This is going to be the x component, We're going to call it negative 6 newtons. Notice it's a negative x component. Why? Because this is positive x direction, and this one's pointing this way, so it has to have a negative x component, right? Now, what is this guy here? I'll draw it kind of parallel to this so you can kind of see it a little bit better. This is called f sub y, the y component. And this one in this problem I'm giving you is also 6 newtons. So this is given to you. We haven't solved anything. I'm giving you the x and y component just like I did last time. And ultimately, I want to figure out what is the magnitude of this vector. So this has a vector, this is vector f. I want to find the length of the vector, and I also want to find out what the angle of that vector is. And there's a lot of different ways to measure the angle, but in this problem, we'll just measure it from the x-axis like we did last time. So we'll call this angle theta. So it's exactly the same situation as the last problem. It's just that in the last problem, the vector was here. There was a very small angle. We had a positive x and a positive y. I want to find the length of the vector. I want to find how much angle we have. Here, exactly the same thing. The only difference is the vector's pointed way over here. So the angle is much, much bigger. Notice it's still measured from the positive x-axis. And because it's over here, it has a negative x component and it has a positive y component. So the x and y component govern which way the thing's pointing, just like any kind of point that you plot, on an xy plane. Now, what we want to do is figure out what the magnitude of this vector is and what this angle is. And to find the magnitude, we do the exact same calculation as last time. It's going to be Pythagorean theorem, which means we take the square root of the x component squared plus the y component squared. Why did we do that? Because this forms a right triangle. This is the hypotenuse. So this squared is equal to this squared plus this squared. We take the square root of both sides to find this guy. So what are we going to plug in here? This is going to be the square root. For fx, it's negative 6. So let's write it as negative 6, but we have to square it. And the y component is positive 6, so we'll square that as well. Now, when you square a negative number, you just get a positive 36. So what you're going to get in here is positive 36 plus another positive 36. And that's underneath the radical. So what you're going to have is the square root of 72. And when you take the square root of 72 in your calculator, you get 8.49. So I want to go ahead and switch colors and just write that down because we've solved the first part of the problem. The magnitude of this vector is 8.49 what? Newtons, because it's newtons in the problem in each direction, so it's newtons acting in this oblique kind of angled direction. So now we want to calculate the other number we need to describe the vector. We want to describe its angle, as measured in this problem anyway from the x-axis. How do we do it? The good news is you do it exactly the same way that you did it before, or exactly the same way that we did it before. But we have to make sure and interpret the results to make sure that we're getting the right answer. So let me go and draw a little line here, and let's jump down here, and let's say this angle is going to be equal to what? It's going to be equal to the inverse tangent of, what did we do last time? We said it was the inverse tangent of this, which was the y value over it was the opposite over adjacent, right? So it's the same thing. It's the opposite side over the adjacent side, opposite over adjacent. All right? So we're going to say opposite side, just to make it clear, is fy and fx. Opposite over adjacent of that triangle. And it's going to be the inverse tangent, right? Well, let's do it this way. Let's say that, let's make it, what I really want to tell you is that, go up here. I don't want to erase that. The tangent of that angle is going to be equal to fy over fx. The tangent of the angle is the opposite over the adjacent side. So if I want to find the actual angle, I have to take the inverse tangent of both sides, exactly what we did before. So what I'm going to do is I'm going to take the inverse tangent of what? 6 is the y component. What is the x component? Negative 6. So you have to put negative 6 on the bottom. So which means you have the inverse tangent of what? 6 divided by negative 6 is negative 1. Okay? So if you go into your calculator and stick negative 1 in and take the inverse tangent, what are you going to get? Your calculator is going to give you negative 45 degrees. Negative 45 degrees. Then I'm always telling you, take your angles that you get from the calculator and go back and look up here and say, does this make sense? And you look at that and you're like, what does that even mean? Well, you got to remember, the calculator is always going to give you angles back, measured from the x-axis. Positive angles go like this, this direction as I have drawn it, right? We call that counterclockwise. That's positive angles. But if you ever get a negative angle, it still means you start from here, but you're going this direction. So really, the calculator told you that the answer was 45 degrees, not this way, 45 degrees below the x-axis, like this, pointed this way, which clearly isn't right because the vectors pointed this way, completely opposite on the other side of the chart than what the calculator told you. So at this point, you go back, you type the numbers in, you type the numbers in, you type the numbers in, you get same answers, and then you start getting worried and scared and and then you lose your confidence, okay? What is happening here? What's happening here is you always have to check your angles that you get out of the calculator. Here you got an angle that doesn't seem to make sense. Why did it give you that? Because when you did this guy right here, inverse tangent of 6 divided by -6 is the inverse tangent of -1. The calculator is always going to assume that your angle is going to be somewhere over here. So in other words, we really have a vector that's here at y is equal a positive value of 6 and x is a value of -6. When you divide them, you get -1. But think about it. If you had a vector pointed down below here, he would have a positive x component and a negative y component. So if the vector were actually down here, if you had a y which was negative and an x which was positive, you would divide -6 divided by 6, and you would still get -1. So if you did have a vector down here, and you divided the y component divided by its x component, you would get the tangent of -1, or the inverse tangent. This should be an inverse tangent of -1. So that would give you the correct angle measure in that case. So what am I trying to say here? In a nutshell, when you do inverse tangent on a calculator, the angle that you get back is always going to be somewhere on this side. It's going to be a negative angle it's going to give you over here if the inverse tangent is negative, or it's going to give you a positive value here. What you have to do is look at it and say, okay, this doesn't make sense. My vector really isn't over here. It's way over here. How do I fix the problem? What you have to do is don't circle this. You say, no, that's not actually theta. The number 45 is correct, but what I have to do is add 180 to it. So let me do it this way. Instead of doing it like that, I'll say it's going to be -45. That's my original angle I calculated, right? I'm going to add 180 to it. Why is that? Because the calculator's telling me the vector's down here, but I know the vector's not down here. I'm going to add 180 degrees, which is going to be halfway around the circle, so it actually is pointing in the way that I know that it's pointing. The angle, in other words, is not really down here. It's really 180 degrees up here. So whenever you do that, you're going to get -45 plus this, you're going to get 135 degrees. And that's going to be the angle. So when you calculate the magnitude, you're always going to get the same number no matter where the thing is pointed. Everything's going to be fine. You're going to get, in this case, 8.4 newtons, 8.49 newtons. Whenever you calculate an angle, anytime you do an inverse tangent, the bottom line is, in this case, it always causes a problem when you have one of these guys or some mixed sign here. Because in this case, in my problem, I had a positive y and a negative x. That's why it was over here. When you divide them, you get a -1, so you take the inverse tangent. However, if my vector really wasn't there, if it was really pointed down here, which is what the calculator is going to assume, what would it look like? It would be -6 for y, +6 for x. Well, I would divide that, I would get inverse tangent of -1. In other words, if I take inverse tangent of -1, the calculator doesn't really know if the vector is here with a positive x and a negative y, or if it's actually here with a negative x and a positive y. Because in both cases, when I divide them, I get -1. The calculator has no idea. You're just typing a -1, taking the inverse tangent. It doesn't really know if you had a -1 here because of the mixed signs and the components was because the vector's down here, or if the mixed signs and those components were because the vector's really over here. So that's why when you take the inverse tangent, you have to take what it's giving you and ask yourself, is my vector really down there or not? And if my vector's not really down there or not, it's giving you that useful information. You say, well, I'm going to add 180 degrees to bring it back over here. And that's going to be the answer. Let me say one more thing before closing. I'm kind of harping on this a lot because it's something that confuses a lot of people. The reason it gave you 45 degrees down like this is because, think about this. We're now saying that this angle theta is 135 degrees as measured from the x-axis, okay? So let me ask you a question. If I know this is 135, what is this angle? That angle inside of this triangle, what is that? Well, if this thing is 180 degrees all the way over here, then if I subtract 135, that should give me that angle. So if I take 180 minus 135, what do I get? If you do that, you would get 45 degrees. So this angle actually inside here is 45 degrees. Doesn't that look an awful lot like what the calculator gave us? So you see, the calculator is not giving you random stuff. It's basically telling you that the angle is actually 45 degrees to the x-axis. It just doesn't actually know if the vector is really over here or if it's really down here with a negative angle. So what it does is that it's programmed, it's not just that the calculator is programmed this way, it's just how the inverse tangent function is defined to be. Whenever you take the inverse tangent of anything, it can only give you an angle from here in the negative x, or the negative angles, all the way up, negative pi over 2, or negative 90 degrees, all the way up to positive 90 degrees. It's only going to return that, okay? But if your vector actually lies in another quadrant, then you may have to add 180 degrees, which is pulling it all the way around the other side of the unit circle so that it would have an absolute value angle the same as what it gave you. That's a lot of theory, and if it confuses you, I apologize. I'm just trying to make it clear to you. So what we're going to do in the next section is we're going to do 2 more examples. In this case, we did a vector here, calculated its magnitude and angle. There was no ambiguity over here. We looked at the answer, we said this makes sense, so I'm good. Over here, we did a quadrant over here. We calculate the inverse tangent. We have to look at it and say, well, wait a minute, it's actually not down, it's not negative 45. We're going to add 180 degrees to bring it up over here. That'll be the angle measure there, and then we get 135. Now, in the next section, we're going to do a vector if it exists over here and a vector exists over there in the other 2 quadrants, and we're going to do exactly the same thing. We're going to take the inverse tangent to find the angles, and if those angles don't agree with our drawing, with where we know the vector is, then we might have to add 180. That's the bottom line, to pull the angle of the vector in the right way, because the calculator is basically always assuming your vector is pointing somewhere over here. That's the way it's programmed, and if your vector isn't, then you might have to use the answer and kind of adjust the angle appropriately. So follow me on to the next section, and we will do that right now.